In module 6, we will continue with our discussion on PPS with and without replacement sampling, mainly with respect to PPS without replacement, and we will talk about formation of the estimators. As I said, in the context of exercises, we have Desraj estimator, which is based on averaging of E1 and E2. E1 is based on the first unit, E2 is based on the second unit using some kind of conditional argument, and it generalizes to any number of sample observations by PPS without replacement sampling. So, in a way that avoids computation of pi I and pi ij and application of Hurwitz-Thompson estimator, for example. There is a tremendous development in the context of PPS sampling when we talk about Desraj estimator. So, let us see what is in store for us in this module 6, continuing with PPS without replacement once more. Note that in the context of PPS with replacement sampling, the individual estimators YT over PT, they behave like what we call IID, and therefore the computation of their average towards estimation of the total, then the variance and the variance estimate, everything becomes very routine. So, this estimator in the context of PPS sampling was proposed long time back by Hansen and Hurwitz, and it is known in the literature as Hansen-Hurwitz estimator HHE, averaged in the context of with replacement PPS sampling. Now, as I said, in the context of without replacement sampling, the estimator based on averaging of E1, E2, E3, etc., that is known as Desraj estimator.
Sir, I'm feeling a bit uncomfortable with the estimator like YT plus YS over 2, since it is dependent on the order of the draw of the sampled units, T followed by S. After all, once the survey statistician got access to the pair of observations, YT, YS, the estimator should not be order dependent. What if somebody hides this information to the statistician? Is then the statistician handicapped?
It is a very good point indeed. First, let me correct what is written over there. So, you are feeling uncomfortable because the estimator is based on E1, ET and ES. It is ET which is YT over PT, and it is E1 which is YT over PT, and it is E2 which is YS over PS over 1 minus PT together with YT. So, this is so what is written here is not true. It should be E1 plus E2 by 2 as we are saying. That is the Desraj estimator. Yes, you have a point, because the computation of E1 depends on YT, the computation of E2 depends on YS followed by YT. Therefore, it is order dependent. So, after all, once the survey statistician got access to the pair of observations, estimator should not be order dependent. That is very true. But in our case, we are calling E1 and E2, both of them are order dependent. That is a very good point. Fortunately, this has been thought out by the survey statisticians long time back, and the concept of symmetrization was coined. So, what is the big idea? You call a symmetrized estimator and you define it as the estimator T hat based on the ordered sample T followed by S. That is what we have been doing. That you multiply it by the probability of getting T followed by S, which is PT times PS over 1 minus PT. And then you look to the reverse side. Imagine S came first and T came second, then your estimator would have been order dependent in the order S comma T, and the estimator would have been T hat S comma T y. And that you multiply by the corresponding probability of the ordered sample S followed by T, and then you divide by PTS plus PST. In a way, you symmetrize your estimator. So, note that the Desraj estimator is order dependent. That is only the first term, T hat TS. But you think, as you said, you think of the other way, the first S would come and then T would come, then it would have been T hat ST. You take their average by using the corresponding probabilities. This is called symmetrized version of Desraj estimator, and this was suggested by Murthy. Here PTS, as I say, T followed by S, PT times PS over 1 minus PT, and PST is PS times PT by 1 minus PS. This is the estimator computed above using the order TS of the units. So one is T followed by S, other is S followed by T. Combined estimator is known as Murthy's symmetrized estimator. This concept applies naturally to higher values of n, though the computations get highly involved, because if you are talking about a sample of size 3 and the sample units are T, S and R, you have to talk about all 3 factorial permutations and frame estimators like T of TSR, T of TRS, T of RS, T, etc., all 3 factorial, get the corresponding estimators and then take their average, etc. It becomes computationally very involved. So I suggest you derive explicit expressions for T hat symmetrized, at least for a sample of size 2, and see how it looks like, and then try to compute the variance and the variance estimate. These are standard exercises.
Sir, I'm tempted to make a remark at this stage. As you said, the genesis of an equal probability sampling is to be able to utilize some sort of size measurement available for all the population units up front. Not only that, it carries a sense of positive correlation with the study character. Otherwise, why would one like to associate the normed size measures with the selection probabilities at each stage of the sampling process?
I don't get your point. Do you mean to say inclusion probability and also the joint inclusion probability should ideally have something to do with the size measures?
In other words, I expect something like this to happen. Inclusion probability increasing in p-values, joint inclusion probability also increasing in the p-values, in some sense. No, not very sure. What I want, well, maybe I'm confused.
That's okay, I will clarify the issue. Yes, there are several studies along this direction, so your query makes sense. Let us set some standard notations at this stage. Pi i's are the inclusion probabilities as usual, and pi ij's are the joint inclusion probabilities, referring to with or without replacement sampling. Then it is interesting to note that under both types of sampling, pi t and pi s, they bear the same relation as pt and ps. P's are the normed size p values, normed size measures, and pi's are the inclusion probabilities. Whether it is with or without replacement, pi t, the inclusion probability of unit t, will be at least as large as the inclusion probability of unit s if the corresponding pt is at least as large as ps. This is an if and only if statement. Similarly, if I am talking about t and s as against that t and r, joint inclusion of t and s will be more than joint inclusion of t and r if between ps and pr there is a corresponding relation, ps greater than equal to pr, whatever be the unit t. So the common unit t can stay idle and the inequality will hold depending on the relation between s and r. More general results are also known in this context. There are interesting studies like these, so your question makes perfect sense. Let us divert our attention to a very general class of sampling methods and develop related estimation techniques. Do you realize that a sampling method for a fixed size little n in a way attaches positive probabilities to all or a subset of samples of size n no matter how? In other words, there may be many ways of assigning the probabilities to these samples of size n. We know for sure we have without replacement, stratified without replacement for a total sample size n across L stata, many such examples of sampling with no auxiliary information on any covariate, etc. So there are many sampling designs which attach probabilities to all or a subset of n chosen samples if we are talking about a fixed size little n.
That's very interesting. So we need not pay much attention to the mechanism of assigning the probabilities, but we must make sure that all units are covered.
Yes, I know what you mean. Make sure first order inclusion probabilities of all capital N population units in the population are strictly positive. Is that what you had in mind?
Yes, sir, precisely so. Maybe, let me think, maybe a bit more than that. Also, same for pairwise joint inclusion probabilities as well. Is that not too much to expect? Maybe we don't need that.
Okay, let's see. Recall the notations pi i's and pi ij's. Tell me, why do you require pi i's to be all strictly positive? These are the first order inclusion probabilities. And in a way, you have the idea that they all should be positive no matter what the underlying sampling design is. So why do you feel pi i's should be strictly positive? What if?
Sir, loosely speaking, pi 1 is 0. For example, suggests not even a single sample includes number 1, and hence unit number 1 can never be observed according to such a sampling method. So essentially, y1 cannot be viewed ever. So it seems we are not in a position to unbiasedly estimate the population total. Am I correct? Sir, in my arguments I said loosely speaking.
What if all the pi i's are strictly positive? Any clue as to how to estimate Ty unbiasedly?
Sir,
Let's try to understand. You are given a prescription of a sampling design, entirely arbitrary sampling design, nothing like simple random sampling with or without, nothing like stratified, nothing like PPS with or without. These are all formula driven. Nothing like that. Just you are given a prescription of sample probability, a sampling design, where you find that all the pi i's are positive. All the first order inclusion probability strictly positive. Do you have any clue as to why and how you can estimate capital Ty unbiasedly?
Sir, that should be possible. Apparently I do not see any obvious contradiction, but let me try. T of y is summation yi, which is summation yi over pi I times pi I. This serves as an identity and it is valid since pi I is more than 0 for each I. Once unit number I has been sampled, yi has been observed. So I can compute yi over pi I for every unit I
in my chosen
sample. What if we simply take the sum over all sampled units? I mean, we propose t hat of y as summing I and s yi divided by pi I. Does this make any sense at all? How do I prove unbiasedness for this estimator of ty? What is unbiasedness after all? Well, we have to take the expectation first. What is the contribution of yi over pi I in the overall expectation? For every sample s, that means contains a unit I need to use its chance of selection, that is, say, p of s, and add them up. Well, that means pi I, so by definition, contribution of yi divided by pi I amounts to yi divided by pi I times pi I, which is yi itself, and that seems to be true for each I, since pi i's are positive for each I from 1 to n. Okay, I think I'm pretty sure this is the case.
You are very right. That is indeed what is happening here. We will see how to continue from this thing in the next module. So to conclude, in this chapter we coined the terms Hansen-Harvey's estimator, the estimator based on PPS with replacement sampling, and then Desraj estimator, the estimator based on PPS without replacement sampling, and then Murthy's symmetrized estimator, which is the symmetrized version of Desraj estimator. Therefore, in the process we mentioned about PPS without replacement sampling, the sample drawn in a specific order, order based estimator, unordered estimator, and then we mentioned about the very general sampling design. So, if we do not have any structured sampling design, for an arbitrary sampling design which is a collection of samples and corresponding probabilities, the probabilities add up to 1, we can always compute pi I, pi ij, etc. First and second order inclusion probabilities. What do they mean in terms of the estimation problem, variance estimation problem, mean estimation problem, etc. We are heading towards that, and all we could see is that if pi I is positive for every I, all the units in the population have first order inclusion probability strictly positive, irrespective of the nature of the sampling design or the sampling scheme, then we can always estimate unbiasedly the population total, and we are good in a way. You have argued very cleverly why we can provide an estimator of the population total if all the pi i's are positive. And you also mentioned in a way that if some pi I is 0, then there is a practical difficulty in estimating the population total, because if pi 1 equal to 0, there is no sample at all which gives the possibility of observing the unit 1. Therefore, y1 is totally unobservable. But the population total Ty that very much includes y1, you can never have an identity giving Ty equal to expected value of the estimator. No estimator, no part of the estimator will involve y1, because estimators are based on samples. So that explains logically why pi I positive for all I is necessary and sufficient for estimation of the population total. We will start from here, and in the next module we will take up a lot of related issues. Meanwhile, in this module, let us be satisfied with some questions and MCQs. So, in this module we have 4 questions. Let me read out. The question number 1, write down explicit forms of symmetrized Desraj estimator under without replacement PPS sampling for small n equal to 2 and small n equal to 3. These are straightforward problems. For small n equal to 2, our sample, if I call the sample t comma s, then the Desraj estimator will be one based on t comma s, another estimator will be based on s comma t, and we have to do the symmetrization by using Murthy's formula. That will give you symmetrized Desraj estimator. When it says n equal to 3, there are 3 units coming up, t, s and r. There are 3 factorial or 6 possible classifications, or 6 possible orderings. For every ordering you will get 3 estimators we called E1, E2, E3. We have to take their average. That average will represent 1 for every single permutation, and there are 6 possible orderings. We will be getting 6 possible estimators, and then we will have to take their average. That will give the symmetrized Desraj estimator. So, notionally and notationally, these are pretty straightforward in our mind. We have to sit down and write. It is a very straightforward problem. Question number 2. Also in question number 1, write down an expression for the variance of the estimator for n equal to 2. Work out its unbiased estimator as well. This is a good question. You work out the variance of the symmetrized Desraj estimator. Just go follow the definition of variance and then work out unbiased estimator. Follow the definition. Question number 2 is not only just algebra, it is more involved in the sense of concept. So, that is a concept bearing problem. Question number 3, under with replacement PPS sampling, establish the claims. These are pretty straightforward algebra, very simple. It relates to pi t, pi s according as pt and ps, and next one is pi ts, pi tr according to ps and pr, t being the dummy variable here. So, these are again very straightforward problems. You know the expressions for all these quantities under PPS with replacement sampling. That makes it easy to work out. Establish the same as in question 3 for without replacement sampling for sample size n equal to 2 and n equal to 3. Under without replacement sampling, in the text somewhere we talked about expression for pi I and expression for pi ij for sample size 2. We did not even write expressions for pi I and pi ij for sample size 3. So, this one says for sample size 2, once you have the expressions, you verify the inequalities in question 3 in terms of pi I and pi ij, and for sample size 3 as well, you verify these quantities. So, there is more algebra involved. Conceptually, it is straightforward. It is more algebra involved in the expressions for pi I, pi ij's as well as in establishing the inequalities, but it is more in the form of algebra. The only conceptual problem was problem number 2. Let us look at MCQ 1. Please read it out.
It is desired to draw n without replacement sample in capital N small n, such that for given positive valued normed size measures P1, P2, and Pn, the inclusion probabilities pi t's and pi ts's satisfy the relations pi t is proportional to pt for each t, and pi ts is proportional to the product pt ps for each t unequal to s. A. This is not possible unless the PTs are equal. B. This is possible by suitably selecting the PTs not all equal. C. This is possible whenever n is 2 without any further condition. And D. This is possible only when n is 2 and PTs are all equal.
It's a very good question, very good problem. The point to note is the highlight to be made is on without replacement. The moment you say it is without replacement sampling, and you are referring to a sample of size little n, and you are referring to pi I, pi ij, etc., you recall some of the relations involving pi i's and pi ij's that were set forth before in the context of without replacement sampling. It said summation pi I equal to little n, summation pi ij over all I and j, that is n into n minus 1, etc. There are three relations exhibited before involving pi i's and pi ij's. Keep those relations in view and then try to resolve this question. It is a very good question, but you need that background information all the time. What is the next one?
It is desired to draw without replacement capital N small n sample such that for given positive valued norm size measures
P, etc. m times,
and Q n minus
yeah,
n
so
times.
for m units it is P, and for n minus m remaining units it is Q. So the norm size measures are in two groups, P all the time for some of them and Q for the rest.
The inclusion probabilities pi t's and pi ts's satisfy the relations 1. Pi t is proportional to p for each t 1 to m, and is proportional to q for each t m plus 1 through n. And pi ts is proportional to p times q for all 1 less than t less than m less than s less than equals capital N. A. This is not possible unless...
So they are making some statements to start with, that if the without replacement sampling is made in a way that there are two groups of population, the first group of m, they behave almost identically, and the next group of n minus m, they behave identically. Seemingly they are behaving identically in two groups. Then they are making a statement like pi also, the inclusion probability first order also will behave in the same manner, and second order inclusion probabilities also will behave more or less along the same manner. So these are the statements made, and the question is whether it is possible or not. There are four alternatives given. Good question. Think it over, please. What is the next one?
It is desired to unbiasedly estimate finite population total T of y by drawing a without replacement capital N small n sample. It is decided that only one draw out of n draws will enable the statistician to draw unit number 1. For the other n minus 1 units, there is no such restriction. With this information, it seems impossible to go ahead and meet the requirements. True, false, true, but variance estimation could be a problem, and true and variance estimation is not a problem even when small n is 2.
Bah. So let's try to understand the problem. It says we are referring to without replacement sampling, but then it has been decided that only one draw will enable the statistician to draw unit number 1. So for example, the very first draw, I can have a selection of one unit out of capital N units, but the first unit has a positive selection probability so that it can come. In all the other draws, the first unit has 0 selection probability. That is what it says, that it can be included only in one out of so many draws. So that is how you have to understand the implementation of the problem, how to implement the sampling design. Given this situation, is it true that you can still estimate the population total with variance estimation and all that? That is how the problem goes. Interesting problem. What is the next one?
It is desired to unbiasedly estimate a finite population total T of y by drawing a without replacement capital N small n sample. It is decided that only 2 draws out of n more than 2 draws will enable the statistician to draw unit number 1. For the other n minus 1 units in the population, there is no such restriction. With this information, it seems impossible to go ahead and meet the requirements.
So similar problem. This time it says if the sample size is more than 2, you are told that only in 2 draws you have a possibility of drawing the unit number 1. So, take for example, draw number 1, draw number 2. In these two, unit number 1 has positive probability of selection. In all other subsequent draws, it has got 0 probability of selection. Given this type of sampling scheme, do you think that you can estimate the finite population total Ty, and you can go for variance estimation and all that?